Herzlich willkommen zum 11. Extremwetterkongress am Freitag, den 24. September zum letzten Vortrag in der Session Klima, Gewitter und Wirbelstrukturen. Und so I will say welcome to Leigh Orf in Wisconsin, I think. Hello Leigh, how are you?
Hello everybody. This is Leigh Orf in Madison, Wisconsin.
Yes.
And I'm happy to be presenting to you today. My talk has been pre-recorded, so Frank's going to press play, and I'll be here to answer your questions after the talk.
And I'm very happy to have you here at the Extreme Weather Congress, and your lecture will go about simulations of supercells, so we are very interested in, and so welcome in Hamburg, and please welcome, and with was heißt ein Applaus auf Englisch eigentlich? Ja, gut, dann klatscht einfach los.
Hello, my name is Leigh Orf, and I'm an atmospheric scientist at the University of Wisconsin, and today I'm going to talk to you about my research on simulating supercell thunderstorms at large eddy simulation resolution. So I'm interested in supercell thunderstorms because they produce a lot of damage, both in the United States, especially in the United States, but pretty much all over. In Europe too, there's supercells, and they can produce tornadoes. There have been some recent examples of that. So we're all interested in understanding how these things work. Specifically, we want to understand why some storms produce tornadoes and others don't, specifically like long-track significant tornadoes. It's a very difficult problem. And in the United States, we're focusing hard on the window between 30 minutes and 2 hours, getting that forecast improved, which is approximately between the watch and warning issue being issued in the United States. So the way this is being done is with numerical models, and we're using ensembles, and we're doing ensembles now at convection resolving resolution. This gives us a suite of results that we can then do statistical analysis on. Generating accurate initial conditions for these models in general, operationally, is difficult because of the lack of observations, basically. The observations network that we have is not as nearly as high resolution as what our models can do. So if you feed your model at high resolution with incomplete initial conditions, you're going to get a poor result. So it's both the initial conditions and, of course, our lack of physical understanding and our physical parameterizations, lack of resolution. There's a lot of reasons why this is a hard problem, but you know, this is important to get this right. My own personal research is more along the lines of basic science and how supercells work, with the general feeling that once we get that part right, we'll be able to forecast them better. I'm looking at things like what causes tornadoes and what are in above anvil cirrus plumes, how are they formed? And we've made some pretty significant research. We've done some pretty significant research in both of these areas. And it's both occurred only by using HPC resources, high-performance computing resources like the Blue Waters supercomputer or the Frontera supercomputer here in the United States. And today I'm going to talk about LES simulations of tornado-producing supercells, as well as something we just discovered about above-anvil cirrus plumes, which are visible from satellite imagery and are used in the United States, at least, for giving you an idea maybe that a storm's going to be more severe, because about 3 out of 4 storms exhibiting AACPs produce large hail or tornadoes. So I'm using a numerical model. George Bryan at the National Center for Atmospheric Research, he has developed the CM1 model, which is massively parallel, does very well on supercomputers. I've modified it to make the I/O faster and more efficient, and I do a lot of lossy floating point compression in order to save a lot of frames so I can do nice animations and do lots of analysis after the fact. We're using Vapor, ParaView, NCView, and Python standard tools that are out there. We have some of our own custom-built tools that we use as well. And again, I mentioned that we're using the National Science Foundation leadership class supercomputers in the United States. So, big question, why do some supercells produce strong, long-lived tornadoes while others in very similar environments may produce a weak tornado or no tornado? And it all links back to genesis of tornadoes. You know, we're still trying to figure out what really goes on during tornado genesis. There's a lot of conceptual models out there, and it's chaotic, it's kind of random, it's difficult to forecast, but we really need to get to the meat of what's going on. And one way to do that is through numerical work. It's much easier to run a big simulation than it is to get a field project together, assuming you have the computer resources to do the work that I do. We're using a storm that occurred in the United States. The initial conditions are the 24 May 2011 El Reno supercell in El Reno, Oklahoma. This produced a long track EF5. The other scientific question that I'm involved in, I'm going to talk about today, is above annual cirrus plumes, and why do some supercells produce them while others don't? Similar to the tornado problem. What's the underlying formation mechanism? Similar to the tornado problem. And in this case, how useful are above annual cirrus plumes really as nowcasting tools? And why are they useful? What's really the link between what's going on at the top of the storm and the large hail and the tornadoes? That's what I really want to figure out. A colleague and myself and a couple of collaborators have made some great strides in this area I'll talk about shortly. So, results from a large eddy simulation, tornado-producing supercells. So this is the 24 May storm. I'm going to show you some slides. I like to do animations, but on Zoom like this, it doesn't usually show up so well. So I'm going to mostly do stills. I'll do a little bit of animations, but if you go to my YouTube channel, you can see these. It'll look a little better for some of the simulations. We're looking at the processes of what's going on during tornadogenesis and also maintenance. We identified a structure, it's a coherent flow structure called the streamwise vorticity current that is associated with strengthening the low-level mesocyclone and hence making conditions more favorable, we think, for tornadogenesis and maintenance. Anything that can increase the updraft near the ground, you got to think that's good for tornado formation and maintenance because of the stretching term in the vorticity equation and how vertical gradients of the vertical motion are conducive to stretching vortices, vertical vortices. So you can read about the work we did here, the prior work. We looked at these structures. We kind of told a story. We're still trying to peel apart all this complexity, but essentially, when you get this long track tornado and there is a streamwise vorticity current, this thing that we identify that's along the forward flank of the supercell that contains a baroclinically generated horizontal vorticity and also vorticity from stretching. There's a lot of vorticity generated as it approaches the updraft. It's horizontal stretching of horizontal vorticity is what it is. And that's actually a significant generation factor here. So we're still in the process of peeling this all apart, but the SVC is definitely something that's interesting, and it's actually been found in Nature in 2 different papers. You can actually read about the streamwise vorticity current. So it exists. It was found in a model, and then a few years later, it was found in Nature. That's pretty neat from my perspective. So this is going to show you sort of what's going on as the mesocyclone gets really ramped up and the tornado forms. On the left, you're going to see the pressure perturbation field. This is all temporally average data to take away a lot of the complexity. And you can see how it is associated with the SVC, which is noted, and also the strengthening of the low-level mesocyclone. As the updraft gets very, very strong, the vertical gradient of W is also very strong. So this tells the story. So the question is, why is the SVC, why is that pressure perturbation happening? And, it has to do with the ingestion of all that streamwise vorticity. And it's almost all the rotational term. If you look at the decomposition of the pressure term, it's almost all rotational. There's almost no linear term at all in there when you decompose it, as you'd kind of expect. A recent simulation we did was actually at 10-meter grid spacing. And this one is the biggest run I've done to date, 250 trillion grid points. And I'm going to zoom in here and show you the reflectivity field as we get very close. That box is going to be the domain that I show in the next few images. So you see 2 features that both look like they could be forming tornadoes. But actually, there's no tornado quite yet. But let's see how this all works out. So in this image, you're seeing the surface buoyancy. The left flank convergence boundary is noted, and you see the paths of vortices that have already happened to the left within the cold pool. That's where they all are. And what you'll see as this progresses is there's sort of an inflection with the LFCB as it sort of rotates about an axis. So it sounds like, what seems like it's happening is there's a widespread pressure drop associated with the SVC that's kind of causing everything to contract and rotate. And you're seeing it in the buoyancy field, but you're also seeing these tiny little vortices doing their thing as well. And eventually you see vortex mergers going on, and I'll show you this in 3 dimensions a little bit easier. But despite what you might think, the vortex A is the one that becomes a tornado, not the one near the bottom. So we'll do this sort of step by step in 3 dimensions. Vortex A on the left there is first seeing the vorticity field, which is interesting. There's a lot of questions about how tornadoes form from the ground up or whatnot. This seems to imply it's ground up, but it's more complex than that, and that's research that's in progress that I'm still working on. But if this is the view, if you look on the right there, The view on the left is looking towards the south. The view on the right is looking towards the west. So, okay, you're looking, right now, you already see the vortex. It's already been felt. The vortex that becomes a tornado has already been felt. And we're calling it vortex A. As we progress, you see vortex A is strengthening, and there's a new vortex, vortex B, on the left. You can see what they look like in 3 dimensions. But at this point, you're only seeing a tornado condensation funnel associated with the A vortex. Stepping out a little more, we actually get the B vortex actually merges with the A vortex, and then there's a C vortex. So you see how this is going on. There's vortex mergers. At this point, we have a tornado on the ground. It's ramping up. This vortex merger is quite fascinating. You see vortex C is almost growing out of vortex A. Well, it ends up wrapping or coiling into the original vortex, and you'll see that in the next slide. And there it is. So that's pretty cool, and you can actually trace that. When you save data at 5 hertz, you can see this happen, and you can look at the supplemental materials and for this work, and you can see animations of this, and it looks really good. It just doesn't look good on Zoom. too much buffering. So, and now it's a full-fledged big old tornado. You know, at this point, we stopped counting vortices. So, all right, that's an interesting result. But I wanted to also talk about something that is really hot off the press here, and I'm very excited about. And this is a different work, different project, and it's with a faculty, Morgan O'Neill at Stanford University, headed this study. And I'm the guy who did all the simulation work on Frontier and got the data ready, and Morgan analyzed it. We found something pretty interesting. So again, what are these plumes? They look like what their name implies. They're above the anvil of the supercell. There's sort of a wispy cloud that is above the anvil. It's like in the lower stratosphere, upper troposphere. It's something that meteorologists have determined are associated with severe weather, so we're interested in understanding them. And what we've done is we've simulated 2 storms, one that produces an AACP and one that does not, based upon some earlier work at the University of Oklahoma. We basically ran the simulations at 50 meters and just decided to see what happens. And it turns out that we've discovered something pretty big, and this is kind of crazy. This just came out 2 weeks ago. We discovered that it's a hydraulic jump. What happens is, and you can see it in this slow animation I'll do, looking at a vertical cross section through the cloud. And what you see in the top is the moisture field, just looking at QV the moisture perturbation. So you're seeing moist air being kicked up into the stratosphere. There's also ice in there too. But at the bottom, that little sort of smiley face thing, that's the jet that forms the hydraulic jump. It's forming right at this point, basically. You're starting to see all that stuff get kicked up. Now in this sequence, it's in 3D. To the left, you see the overshooting thunderstorm top. And here comes the above anvil cirrus plume. I'm shading the water vapor perturbation field with potential temperature perturbation. So blues are negatively buoyant, reds are positively buoyant. But yeah, look at that thing go. I mean, it's way up there, and you can almost see it if you look carefully. You imagine that the thing on the left, the overshooting top, is an actual mountain, and you've got a downslope windstorm forming a hydraulic jump. Essentially, that's what we see in our simulation. So we have a situation where, to the best of our knowledge, this is the first observed case of a hydraulic jump that is absent topography. So hydraulic jumps are understood to occur in the atmosphere all the time when you have orographic winds, that downslope winds that can cause a jump, and you see turbulence. You can see it in the cloud field. You can observe it. But that requires a mountain. In this case, the overshooting top of the thunderstorm is the mountain. And the winds, under certain circumstances, will plunge down the overshooting top and form that jump. That's a pretty interesting thing. Now, another reason why these storms are studied is because not just as a nowcasting tool for severe weather, but for climate studies, water vapor in the stratosphere or water substance in the stratosphere can catalyze ozone destruction. And that's considered to be a bad thing for various reasons, of course. It could also allow more shortwave radiation to penetrate through the troposphere and heat the surface of the Earth. So there could be a positive feedback associated with these things. If we find ourselves in a climate where we have more intense thunderstorms producing more above anvil cirrus plumes and more hydraulic jumps, shoving more water into the stratosphere, I don't know. I don't know how strong of a feedback that really would be. And it's really sort of outside of my wheelhouse. I'm really excited to be doing work that's more related to climate, the impact of severe weather on climate, and that's Dr. Morgan O'Neill's, that's her specialty. So this is pretty neat, and it also is something other than just tornadoes. But really, the link between AACPs and the strong hail and the tornadoes is of great interest, because if we can actually find out what that link is, what it really means. I mean, we know it's a hydraulic jump that causes the AACP, but what causes the hydraulic jump, the shear profile, the cape, the instability, what does that space look like? Once we figure that part out, I think then we're really in good shape. So, so as I sort of summarize this whole approach, you might say, the main takeaway that I'd like you to have is that I sort of approach my science from the perspective of what can I do with a supercomputer to help us learn things about the atmosphere. So it's kind of backwards from how most people do science, where they have a scientific question they want to answer and they pursue it. Well, I do, but it's like I know that we can do things with these models. So I've spent a lot of time making the model run efficiently on a supercomputer so I can do the kind of studies I want to do. And the main takeaway is that, yeah, you can do this, and it can be pretty big. I mean, by focusing on just data management, I was able to discover something new. And that I'm just trying to make the point that as we get to the exascale and we get more into these bigger machines, bigger problems, data is going to become more of a problem, not less of a problem. So we need to get our hands on data. And it really shouldn't be as hard as it is to do this. I mean, ideally it would not be, but it's not going to get any easier. As we're going to have more data, I think there's going to be tools that are going to help manage this, but at the same time, the data is going to get larger and larger. So it's always going to be playing catch up with the data is how it looks to me. And it will take a while before the work that, I think the work that I'm doing, the pure research stuff, filters its way into the operational world where it's useful to society. But I think it's going to happen, and I am interested in getting back into the lower resolution space, trying to improve those forecasts. In other words, work more towards the operational goals, not just the science goals. So my collaborations also include operational meteorologists, scientists who do weather forecasting. So yeah, it's going to take a while before it makes it out. But anyway, I think I can pause for questions. This talk was recorded yesterday, and I believe I will be able to take your questions right now. So I would like to thank you for your attention and pause for questions. Thank you.
Thank you very much. Thank you very much, Leigh. And so Fragen an Leigh. Ja, da ist eine Frage und da kommt noch eine. So the first question to you.
Hi, Leigh. That was absolutely fabulous. And as a storm chaser and a huge fan of yours, I mean, it was good to see one of these presentations more or less live. It's a bit late here, so I apologize to all of those who want to go home for the questions. But here, I've got two. So the first is these AACPs. As storm chasers, of course, the way we are, you are rarely seeing what's going on while you're chasing on top of the cloud. So you look at the radar, at the satellite image later, and then you might discover it. But I can't remember having ever seen it. So how often does it happen? That's one question. The second is a bit more basic. When you do spin up these simulations, how many attempts does it take you to actually get it to work? Because I can easily imagine it's not going to happen with the first setup. Thanks.
Yes. Thank you for your questions. I'll answer your second question first. It often takes a lot of tries, you might say. And this is an interesting issue because when you see a paper published about a numerical simulation, there's probably been 20 simulations that happen that you didn't see. And what we do as scientists, we have a problem we want to solve. So I wanted to get a tornado to form in a supercell. So I tried really hard to get that specific thing to happen so I could study it. But when it comes to understanding, say, variability of, predictability, then you have to look at the storms that don't produce the supercells. So I like to joke, I've spent most of my career simulating supercells that don't produce tornadoes, even though I was trying to produce them. Now I can produce them, so now it's time to look at the full spectrum. Regarding above anvil cirrus plumes, this is a new area of research for me. I'm not quite sure how common they are, to be quite honest. They are associated, in the United States at least, with the studies I have seen, with severe weather. And the reason why, obviously for storm chasers such as yourself, not useful, right? Because unless you have, maybe you're looking at your device and you see the satellite imagery and you see an above anvil cirrus plume occurring on a storm. That might be useful to you because that might tell you that the chance of severe weather is more likely, because 75% of supercells that exhibit AACPs produce large hail or tornadoes. Now, or, that's a big or, right? Because there's a big difference between a tornado and large hail, depending. But so yeah, this is a kind of a new area. If you think of Ted Fujita and his jumping cirrus from back in the days when he'd fly aircraft and observe the storms from there, he already saw these things. You know, it's amazing what Ted Fujita saw, and he was so insightful. But so we've known about these features for a while, but we're now starting to understand what causes them. And so, yeah, that's, I'm really looking forward to exploring the parameter space for above anvil cirrus plumes so I can at least answer your question more accurately about how common they are in the simulation world, and then, of course, go back to the observational world.
So thank you very much for this answer. And the next question.
Yeah, beautiful simulations, thank you. Can you use your results to investigate the impact of tornadoes on special structures, for example, buildings or anything like that? Are there further investigations than just the basic investigation of the tornado itself?
Yes, and in fact, I wish you were on the NSF panel that's reviewing a proposal of mine. Yes, I am working on collaborating with a wind engineer whose specialty is structural engineering and wind. So I want to take my big EF5 tornado and I want to sort of run it through buildings, or maybe not an EF5 or F5. Wind engineers are more interested in maybe F0 through EF3 or so, because most structural design parameters are not going to be going to survive an EF5 or an F5. So yeah, I'm interested in creating more weak tornadoes so that I can then somehow find a way to link the tornado from the physical model, the cloud model itself, into maybe a different model. And it's really going to be the interface of these two models. And this is turning out to be a really sticky problem, but I think we're going to be able to do it. And it is definitely something that I'm pursuing. I'm going to be pursuing funding for that. I did once and it was rejected, so now we're going to turn it around and try it again.
So thank you very much, Leigh. And in the background, I can see that your next project would like to be a billiard simulation, so you win all the time. Thank you, thank you very much for your amazing lecture. Thank you very much to you, Leigh Orf.